Good morning. Today, I'm going to introduce LDB, which is an efficient latency profiling tool for the multi-threaded latency-sensitive data center applications. This is a joint work with Saeed from USC, Ahmed from Georgia Tech, and Mohammad and Aram from MIT. Nowadays, more and more latency-sensitive applications demand stringent latency requirements. For example, web needs to be responsive so that the user doesn't experience any delays. ML inference tasks like the AI chatbot needs to be interactive. And real-time ad bidding and the high-frequency stock trading needs to make and execute the decision in a blink to beat the competitors. For higher modularity and the better maintenance, a single application is often composed of the multiple RPCs, utilizing parallelism by the multiple machines and cores. And each RPC service is served by the multiple replicas or shards for scalability and availability, which creates a high fan-out traffic pattern. With such a high fan-out traffic pattern, low tail latency of the RPCs are especially important due to the straggler problem, where it needs to wait for the slowest RPC before constructing a response. As a result, optimizing RPC tail latency is a critical building block for the latency-sensitive data center applications. As an effort to minimize the RPC tail latency, an extensive stream of the research has been trying to diagnose and mitigate tail latency in network side, such as Hinside or the Bobscope, which is presented in the previous NSDIs. However, they treat RPC applications as a black box and only can identify which part of the applications has a high tail latency without telling us why. In this work, focusing on the application side, we are trying to profile the latency behavior of the RPC applications to trace down which functions are the most responsible for the high tail latency to enable developers to debug it. Let's consider a very simple key value store application, where key is an integer and the value is a string. Here, we have the one map to store the key value pairs, and there is a global lock to protect the entire map. And we have the request handler, which takes the key value pairs as an input and store them into the map while holding the lock. And there is a background thread that is launched upon program starts and takes a snapshot of the key value pairs for every 10 milliseconds for the failure recovery. In the snapshot function, it records all the key value pairs into the storage while holding the global lock to keep the consistency. In this example, because both request handler and the snapshot function require the global lock, request handler may experience a long wait time while the background thread is taking a snapshot. As a result, if we are plotting the function invocation latency distribution of the request handler, we can see that the 4 nines takes a 60 times higher than the median. In this example, we know that the snapshot function is obviously the root cause of the high tail latency. But it is hard to figure out the root cause in the complex data center applications in the real world. What the most people do for such a performance debugging is to use CPU profilers, like the Linux perf or the gperf tool, and look into which part of the code is using the CPU the most time. This is the output of the Linux perf for the example application. Even though the snapshot function is taking a long time, because it runs so infrequently, it consumes so little CPU. As a result, snapshot function is buried down on the list, reporting less than 1% of the CPU time. Linux perf, as a sampling-based approach with a low frequency, is not suitable for profiling the tail behavior, as the tail events are buried by the average behavior. Now, let me show you a live demo whether the LDB can effectively figure out the snapshot function as a root cause of the high tail latency. Yeah, here we have the example application implemented in C++. And the developers are only required to replace the compilers with the customized one provided by the LDB. And let's run it for profile the request handler for 200,000 requests to see the result. And you can see some kind of metadata, and now the profiling is done. And you can see the output of the LDB here. So it reports the function invocation latency distribution for each functions and each line of the code. For example, here, you can see that the request handler has a very short median, while it has the very high 3.9 latency. And the developers can indirectly infer the information that the high tail latency of the request handler is related to the pthread mutex log and the snapshot function here. And optionally, the developers can tag the request with the lightweight annotation API provided by the LDB. Like in this example application, it only requires the two code changes. The first one is when the request starts, we are tagging the request with the unique request ID. And when the request ends, when the request leaves the machine, we can clear the tag so that the application is not responsible for this request anymore. So with these two simple code changes, this is a kind of the demo dashboard. So we can profile this reports the unique request ID and the equivalent application latency on the right side. And this list reports the 100 longest requests. And also in the bottom below, you can see the various the percentiles. You can see that the median is kind of low, small. And for the interesting results, let's see one of the longest request, for example here. And this one specifically, we focus on the specific request ID. And it reports the timeline for the thread related to the specific request ID. And each graph represents each thread related to the request. For example, in the bottom, you can see that the request handling thread is delayed because of waiting for the pthread mutex log in the most of the time. And on the upper side, you can see that the background thread, which is holding the lock, is delayed in releasing the lock because of the snapshot function. So how could LDB do that? To better understand our approach, let me briefly remind you how x86 stack frame works. In x86 architecture, when a new thread starts, a stack data structure called the stack frame is allocated in the stack memory area. The bottom and the top of the stack are marked with the RSP and the RBP respectively. In this diagram, stack is growing downwards. The function uses a stack for a temporary storage for the local variables. And when a function has another function call, it first backs up the instruction pointer into the stack frame to remember where to return after the function execution. And then save the base pointer of the previous stack frame and update the RBP and RSP. In this way, x86 architecture starts a new stack frame for new function calls. Again, the stack is growing downwards to store the local variables in the function. And for each function call, a new stack frame is created in the same way and is attached to the previous stack frames. When the function returns, it can resume the parent function using the stored base pointer and the return instruction pointers. This stack frame structure forms a singly linked list, which can traverse all the function call chains once we know where to start with the current value of the RBP. Yet here, we focus on the fact that the metadata in the stack frame, including the return IPs and the saved RBP, remain the same as long as a thread is stuck in a bottleneck function. The key idea of the LDB is to sample the stack frames to measure the latency for each function call. As you have seen in the live demo, LDB provides the accurate latency information. With the inter-thread communication records, LDB can pinpoint the root cause of the high tail latency. In this example, LDB not only tells you that waiting for the log is the reason for the high tail latency, but also that the mutex holder is delayed in releasing the log because of the snapshot function. And LDB has a reasonable runtime overhead with a minimal distortion to the original latency behavior. And developers can debug the latency issue interactively with LDB. And finally, LDB doesn't require any special hardware as it can be implemented purely with software. Now, let me dive into the details how LDB can achieve all of this. In LDB, we have a separate thread busy running with sampling the stack frames called the stack scanner. However, this is not enough. We have several challenges to overcome in realizing the stack sampling idea. The first challenge is we need a current value of the RBP to start traversing the stack frame. But we cannot read the register value of another core. To address this challenge, we modify the compiler and keep track of the latest RBP at the designated memory region in the thread local storage. It updates the latest RBP in the TLS whenever the function returns, or a thread has a new function call. Through this latest RBP in the TLS, which is located at the known address, the stack scanner thread can fully traverse the stack frames of the application thread. The second challenge is we need a way to differentiate the stack frames of the two different function calls of the same function. The metadata of the two different stack frames may be the same, even though they are from the two different function calls. For example, the return IP and the saved RBP are the same across the stack frame of the bar function calls here in the for loop. As a result, the stack scanner cannot distinguish between the two stack frames for two different function calls. And the measured latency of the bar function calls can be inflated because of that. To address this problem, we maintain the generation number in the TLS, which is a simple counter incremented by 1 with the new function for every function calls. When a new function call happens, LDB first increments the generation number and then pushes it into the stack before creating a new stack frame with our customized compiler. Now, by looking at the generation number in the stack frame, which is located at a fixed offset from the stack frame, the stack scanner can determine whether two different stack frames sampled are from the same function calls or not. And third challenge is a runtime overhead due to the cache thrashing. Because the stack frame are actively accessed by the application thread for the local variables, and if the stack scanner thread accesses the stack frame too frequently, the application thread performance can degrade due to the cache thrashing. To minimize the stack scanner's access to the stack frames, we focus on the variables in the TLS. The latest RBP value changes with a new function call and the function return, and the generation number changes with a new function call. As long as the two variables in the TLS stay the same, we can safely conclude that the stack frames stay the same. With this intuition, the stack scanner first checks whether the latest RBP and the generation number in the TLS has changed or not. And if they stay the same, it can just increment the latency without traversing the stack frames. Otherwise, it can initiate the stack traversal. With all the techniques, let me dive into how LDB actually measures the latency in details. The stack scanner thread keeps track of the latency and the return IP for each generation number. At initialization, stack scanner thread starts traversing the stack frame using the latest RBP in the TLS. For the stack frame with the generation number sampled for the first time, the stack scanner creates a new entry with a 0 latency and the corresponding return IPs, and keep traversing the stack frame until it reaches the main function. From the following iteration, as long as the latest RBP and the generation number in the TLS stay the same, the stack scanner thread increments the latency of all the entries by the elapsed time, and keep increasing the latency until it detects the changes in the thread local storage. Once it detects a change in the TLS, it starts traversing the stack frames, and again it inserts a new entries for the stack frame with a new generation number. And while traversing the stack frames, if it encounters the previously sampled generation number in the stack frame, it increments the latency by the elapsed time. After finishing the stack frame traversal, if there is an entry whose generation number is not present in the stack frames, LDB concludes that the function has returned and export the events into the event buffer, which is used for the further analysis later. Other than the function latency events, LDB records the other types of events to better analyze the relationship among the latency events, including the synchronization events, thread events, request events when the request tagging is provided, and the scheduling events by the OS scheduler. Please refer to the paper for more details on which types of the events of the LDB is collecting. Through the evaluation, we answered 3 key questions. First, how much is the overhead of the LDB for the real-world data center applications? Second, how fast LDB can report the result? And finally, how portable is LDB? We compare LDB with the 3 existing state-of-the-art latency profilers, Intel PT, COS, and X-Ray. Intel PT is a hardware-assisted processor tracing tool which provides a cycle-level accuracy for the latency profiling. COS is a sampling-based causal latency profiling tool where it measures the function's virtual speedup by intentionally injecting the latency to the other thread than the thread executing a sampled function. X-Ray is a timestamp-based function call tracing system with a static instrumentation by the LLVM compiler. To see how much runtime overhead LTV incurs for the real-world data center applications, we launched the memcached server with the 8 workers and generate the load of the 20% of the system's capacity. Here, for the 2 different workloads, memcached set and memcached get, we showed the end-to-end latency distribution when the different latency profilers are running. COS has the largest overhead, especially at tail, because it intentionally injects delays to measure virtual speedup. X-Ray's overhead is increasing proportional to the number of the function calls, and it has a higher overhead in set workloads. Due to the higher overhead, both COS and X-Ray distort the original latency behaviors. On the contrary, LDB has a comparable overhead to the hardware-assisted approach, Intel PT, with up to the 22% of the end-to-end latency overhead. Even though Intel PT and the LDB has a comparable overhead, Intel PT is not suitable for the interactive debugging. Because Intel PT's raw output is a branch information, and it requires additional decoding to convert those branch information into the latency information, which is very slow, taking up to the 1.8 hours to decode 1-second word trace in a memcached get workload. On the other hand, as LDB's raw output itself is a latency information, it only requires a processing for interweaving the events and calculating the statistics. As a result, LDB only takes up to the 2.7 seconds to decode the 1-second word traces, enabling interactive profiling with a fast result. Next, to demonstrate the portability of the LDB, we measured the throughput achieved by the Quickly, a fast-release implementation of the QUIC protocol with the latency profiling by Intel PT and the LDB. Even though Intel PT shows 4% of the overhead with the recent CPU architectures, older model costs up to the 59% of the overhead. In addition, as an Intel-specific mechanism, it cannot be used for the AMD processors. On the contrary, LDB shows consistent overhead across the different CPU architectures, which is comparable to the overhead of the hardware-assisted approach with the recent CPU architectures. Okay, let me conclude the talk. LDB is an efficient latency profiling tool to diagnose root cause of the high tail latency in latency-sensitive data center applications. With the stack sampling with the generation number, optional request tagging, and the automatic event findings, LDB can profile the application's latency behavior with low runtime overhead, fast decoding time, and the great portability. And thank you, and LDB is available as open source, and I'm happy to take any questions.